Welcome. This video is going to look at the last part of section 9.1 in the Brown SLIB chemistry book and talk about redox titrations. So redox titrations are similar to an acid-base titration in that you have known amounts of both the oxidizing and reducing agent, but you know the concentration of one of the reactants and you titrate it against the other to determine its concentration. So some redox reactions will have a color change that will indicate when the reaction is complete, such as permanganate changing from purple to clear, or chromate can change between orange and green depending upon what oxidation state it's in. Otherwise, if there's no color change, an indicator can be used. And this is a commonly used process in the food and beverage industry, for example, determining sulfur dioxide in wine or vitamin C in a food or drink. So there's three different redox titrations that IB expects you to be familiar with. The first one is titrating iron ion with manganese or manganate ion, and it typically uses potassium manganate, permanganate, in an acidic solution as the oxidizing agent, and then Fe2 plus is oxidized to Fe3 plus. That means that the manganese is reduced to Mn2 plus, and that's where the color change occurs from purple to colorless. So let's look at how you would actually calculate a titration for this. For example, all the iron in a 2-gram tablet is dissolved in an acidic solution and converted to Fe2 plus. When titrated with the potassium permanganate, it required 27.5 centimeters cubed. I'm going to convert that to liters, I think 0.0275 liters of 0.1 molar KMnO4. They want to know the percent by mass of iron in the tablet, and also how will you know the equivalence point has been reached. So for starters, we need the balanced equation for KMnO4 and iron ion. So if we look at this, we have Fe2 plus becoming Fe3 plus, so that's a loss of 1 electron. With permanganate, we have MnO4 minus becoming Mn2 plus. That's a change of 5 electrons. So I add the 5 electrons to the reactant side. Because Mn2 plus does not have any oxygen associated with it, I also add the 4 H2O to the product side. And then I have to add the 8 H plus to the reactant side to balance my charge and atoms. Now, before I can combine the two equations, I have to go ahead and multiply the top equation by 5 so that my transfer of electrons is equal. And then my combined equation here, I see my balanced equation for this titration is 5 Fe2 plus ions plus MnO4 minus plus 8H plus gives me 5 Fe3 plus ions and Mn2 plus ion and 4 water. So how would I use stoichiometry to determine the grams of Fe2 plus that was oxidized? Well, I'd take my 27.5 centimeters cubed. This should be a centimeter here, not decimeter. And I'm going to convert that to 0.0275 liters or decimeters. So that's this reactant right here, 0.0275 liters that we're dealing with. It's 0.1 molar strength. So that means if I multiply these, I'm really starting with 0.002750 moles of MnO4. And when I look at my equation, I see that the iron is reduced in a 5-to-1 ratio. Actually, it's oxidized in a 5-to-1 ratio with the MnO4. So that means there must have been 0.01375 moles of Fe2 plus that were oxidized in this reaction. Now that I know how many moles of Fe2 plus, I can go ahead and convert that to grams by using my molar mass of 55.85, and that means there must have been 0.768 grams of Fe2 plus that were oxidized. So then finally, what's my percent by mass? Well, 0.768 out of a 2-gram tablet would be 38.4%. And finally, how do I know when the reaction is done? Well, it's the KMnO4 that's purple, so that would be in my burette being dropped into my iron solution. And as it drops in, we would see purple persist and then turn clear as it reacts with the iron. And at some point, the KMnO4 will have no more iron to react with, and at that point, the flask will remain purple. So when the iron solution turns from clear to purple, we know our titration is complete. So here's another redox titration. KMnO4, KiO3, K2CrO4, and NaOCl are all oxidizing agents that will oxidize iodine ions. So if you have two iodine ions with one of these oxidizing agents, you can end up with I2, and then that will also produce a reducing agent if it runs in reverse. And then the I2 can be titrated with something called sodium thiosulfate, Na2S2O3, and determine your concentration. And for this reaction, starch is actually used as the indicator because the sodium thiosulfate will react with the iodine until there's no more sodium thiosulfate available, and then the starch will react with the iodine to turn a deep purple and let you know you've used up all your sodium thiosulfate. So the overall reaction with the sodium thiosulfate is two thiosulfate ions reacts with one iodine molecule to produce two iodine ions and then S4O6 ion with a 2- charge. So the iodine ion is reduced while the sulfur is oxidized. So here's an example of how this titration is used. Bleach contains sodium hypochlorite, NaOCl. So OCl is the ion we're going to be interested in here, which reacts with iodide ions in an acidic solution. So you see that the OCl minus and the 2I minus will react to produce iodine molecules, chlorine ion, and H2O. So once we have the I2, we can react it with sodium thiosulfate to find out how much I2 there was. So in my example down below here, a 10-centimeter sample of bleach was reacted with a solution of excess iodide ions. So that would be up here. So reactant our bleach, 10 centimeters cubed, was reacted, and it produced some iodine. This iodine that's produced up here is then titrated with the S2O3 ion, and it required 38.65 centimeters cubed, or 0.03865 liters of a 0.02 molar solution. So it says determine the concentration of OCl in the bleach. So what we're going to do is we're going to determine how many moles of the S2O3 did we use, and then we'll be able to convert that to moles of I2 because it occurs in a 1-to-2 ratio. And then looking back to the previous reaction, we see that the I2 and the OCl minus occur in a 1-to-1 ratio. So this is sometimes called a back titration, where we work our way back to the OCl minus and determine the concentration of hypochlorite in the solution. So as I indicated up above, I'm going to take the 0.03865 liters times 0.02, and I determined that I have 7.73 times 10 to the minus fourth moles of, that's my S2O3 ion. And that then occurs in a 1-to-2 ratio with the iodine, so that means I must have half that much, or 3.865 times 10 to the minus fourth moles of iodine. And because in the first equation we saw that the hypochlorite and the iodine occur in a 1-to-1 ratio, this is also my moles of hypochlorite. So what's my concentration in moles per liter? Well, it's 3.865 times 10 to the minus fourth moles in 10 centimeters cubed, which is 0.010 liters. So if I go ahead and divide that, that would be a concentration of 3.865 times 10 to the minus second. The third titration that IB talks about is something called the Winkler method, and this method is used to determine dissolved oxygen. And this one probably has the most environmental implications. The previous one is used a lot in foods, but the environmental implications is that dissolved oxygen in water is an important indicator of how healthy that water is, or of its water quality, how polluted it is. The more oxygen, the better. When oxygen levels go down, it means oxygen's being consumed to get rid of bad stuff in the water instead of for aquatic life. So as pollution in water increases, demand for oxygen increases, and the dissolved oxygen levels fall. So this BOD, or biological oxygen demand, is a common way of measuring the degree of water pollution or the water quality. BOD is defined as the amount of oxygen used to decompose the organic matter in a sample of water over a specific time and temperature. And it's generally 5 days and whatever the current temperature is. So if you have more organic matter, then the amount of oxygen used is going to be higher. The demand is going to be greater. So that's a bad thing. So what's increasing the demand in our lakes? It's all the nitrates and phosphates being used on fertilizers, both on private lawns, farms, etc., which is why we see more and more algae blooms in our area lakes. And you may or may not know that algae blooms can start the process of eutrophication, or what's known as the dying of a lake, because the algae covers the surface, so sunlight can't get through and photosynthesis can't occur, so more things die off, which demands more oxygen and creates more algae blooms. And you get into this cycle where the lake cannot regain its health. So what's the titration used? Well, the Winkler method uses redox titrations by using 3 different reactions, and they're actually similar to the 3 we just looked at. Mn-2 is actually oxidized back to MnO2 to permanganate. Iodine ions are added and oxidized by the MnO2, and then the resulting I2 is titrated with thiosulfate. Now, we could look at these 3 individual steps, and the book does, and you're welcome to do that, but really what you need to know is 1 mole of O2 in the water will use 4 moles of Na2SO3 in the titration. That's the way it breaks down, 1 to 4. So if we were told we had a 500 centimeter cube sample of water collected and tested for dissolved oxygen by the addition of MnSO4 in a basic solution, followed by the addition of acidified Ki, the titration then required 12.5 centimeters cubed of 0.05 molar Na2SO3 to react with the iodine, calculate the dissolved oxygen in grams per decimeter cube. We don't have to write down all the equations for this. What we need to do is take our 12.5 centimeters cubed and change it to liters, multiply by the molarity, and figure out how many moles of Na2S2O3 was used. So since 6.25 times 10 to the minus 4th moles of thiosulfate was used, I can multiply that by the 1 to 4 ratio of O2 to the thiosulfate and assume that that means 1.56 times 10 to the minus 4th moles of oxygen was present. So then to get that to grams per decimeter cubed, I change my moles of O2 to grams, multiply by 32, and I get 0.005 grams. I divide the 0.005 grams of oxygen by the liters of water used, which is half a liter, and I can assume my O2 level was 0.01 grams per liter.